In a world of complex chemical reactions, one cell rises to the challenge. It takes the hidden power of chemistry and transforms it into pure, raw electricity. Get ready, because this is the story of the galvanic cell.
Okay, so let's get right into it. It all starts here, in the classroom, with a question from Professor Verma. It's a question that kind of makes you scratch your head, right? Just like Raju here. But of course, toppers like Priya are already nodding along. The big question is, how in the world do we get electricity from a simple chemical reaction?
Well, the answer to that question lies with our hero for today's lesson. So let's get right to it and meet the galvanic cell, the champion that literally makes its own power. So what is this thing officially? Well, according to your textbook, a galvanic cell, sometimes called a voltaic cell, is an electrochemical cell where electrical energy is produced from a spontaneous chemical reaction. Now, those two words are absolutely key: produced and spontaneous. It means this thing happens all by itself, no help needed. The simplest way to think about it is like this. It's a clever little device that takes all that hidden energy locked away inside chemicals and, boom, it turns it into electrical energy you can actually use. You don't need to plug it in or anything. It's its own little power plant, just like this battery right here.
All right, so every hero needs the right equipment, right? So now we're going to see how we actually build our champion, piece by piece. Pay close attention here, because this is exactly what you'll need for your diagrams and your practical exams.
You know, the basic setup is actually pretty simple. You start with two separate containers or half cells. In each one, you've got two things: a strip of metal, which we call an electrode, and a solution that has ions of that same metal. Then, you just have to connect the two halves. You do that with an external wire on top and this other special thing called a salt bridge.
And here it is, the most famous example of all time. I guarantee you've seen this in your textbook. It's called the Daniell cell. In one half cell, you've got a zinc electrode sitting in a zinc ion solution, and in the other, a copper electrode in a copper ion solution. That's it.
Okay, our cell is built, the stage is set, and now for the main event. This is where the real action happens. It's where the chemistry turns into electricity, and let's be honest, it's where all your exam marks are hiding.
So let's break it down. The whole process kicks off at the anode, which is the negative electrode. In our example, that's the zinc. The zinc is more reactive, so it undergoes something called oxidation. All that means is it loses 2 electrons. It goes from being a solid zinc atom to a zinc ion, and it just dissolves into the solution. You can almost feel bad for the little guy.
So what happens to those 2 electrons that zinc just lost? Well, they don't just disappear. They travel up the electrode, through that external wire, all the way over to the other side, to the cathode, which is the positive electrode. And over there, the copper ions in the solution are just waiting to grab them. They happily accept the electrons in a process called reduction and turn into solid copper atoms.
And when you put those two halves together, you get the overall reaction for the entire cell. Solid zinc plus a copper ion gives you a zinc ion plus solid copper. It's really just a simple transfer of electrons from one place to another. And yeah, just like that student down there, you suddenly realize it's all connected.
Okay, this next part is super important because it trips a lot of people up, so listen carefully. The actual electrons, the little negative particles, they flow from the negative anode to the positive cathode. But, just by convention, scientists decided to say that current flows in the opposite direction, from positive to negative. So just remember, electron flow and current flow are opposites. Don't mix them up.
So, we've talked about the anode and the cathode, the main stars of the show. But remember that other piece we mentioned? It's time to shine a spotlight on the unsung hero of the galvanic cell, the salt bridge. I'm telling you, it looks simple, but without it, the whole show grinds to a halt.
So what is this thing really? Well, it's pretty much just a U-shaped glass tube, and inside it's filled with a special electrolyte, like potassium chloride, that's mixed into a jelly, kind of like agar-agar. The most important word there is inert, which means it does its job without interfering with the main reaction. And right on cue, our friend Raju is asking the exact question you should be asking. But sir, what does it actually do? And that is an excellent question, because its function is absolutely vital.
So, the salt bridge has a few really critical jobs. For one, it completes the electrical circuit on the inside. But its main job, the most important one, is to maintain electrical neutrality. See, as the reaction goes on, charges would build up in each beaker and stop everything. The salt bridge lets ions move between the solutions to balance things out, keeping the electricity flowing. Oh, and it also keeps the two solutions from mixing, which is a nice bonus.
All right, so you get the mechanics of how it works. Now it's time to learn the secret language of electrochemistry. Let's figure out how to write cell notation, which is basically the shorthand way to describe a cell that'll make you look like a real pro.
And you know what? The rules are actually really simple. First rule, the anode always goes on the left and the cathode always goes on the right. Easy. That single vertical line, that just shows a boundary between two different phases, like a solid electrode and a liquid solution. And that double vertical line right in the middle? Yep, you guessed it. That's our hero, the salt bridge. And here's what it looks like all put together for our Daniell cell. You've got the anode stuff on the left, solid zinc, a line, then zinc ions. The double line for the salt bridge, then the cathode stuff on the right, copper ions, a line, then solid copper. See? Just like Priya's thinking. Once you get it, it's easy peasy.
Okay, the final bell is about to ring. It's time for a lightning-fast recap to make sure you've got all the most important points locked in your brain for the exam. Let's do this.
Now, one of the all-time favorite exam questions is to ask the difference between a galvanic and an electrolytic cell. So let's run through it fast. Galvanic is spontaneous, it turns chemical energy to electrical, it needs no battery, and its anode is negative. Electrolytic, it's the exact opposite on every single point. This table right here is your secret weapon for those multiple choice questions.
Need some quick, punchy answers for that short answer section? I gotcha. What does a galvanic cell do? It produces electricity. What's the salt bridge for? It maintains neutrality. What happens at the anode? Oxidation. And at the cathode? Reduction. Simple, to the point, and get you full marks.
And look, if you only remember one single thing from this entire explainer, please let it be this. The G in galvanic is for generates. A galvanic cell generates electricity. Drill that into your head.
And for the final exam tip, here's a killer mnemonic straight from the professor. Just remember the word lone, L-O-A-N. In a galvanic cell, the left side is where oxidation happens, it is the anode, and it has a negative charge. Lone. Remember that, and you will never mix up your anode and cathode ever again. Good luck.